Hello everyone, my name is Farzad Tashtarian. I'm going to present our recent paper accepted by the ELSIN conference, a distributed delivery architecture for user-generated content live streaming over HTTP. First, we take a look over challenges of the user-generated content, and then we define the address problem in this study. And also we propose the QuaLA as our main approach, and then we take a look over results and conclusion future work. Regarding the advancement of a cellular network, live user-generated content or UGC has become very popular in these days in different applications, for example in gaming and e-sport. And we know that majority of UGC services use HTTP based adaptive streaming or HAS for communicating with the server, or for example CDN origin server. Here in the study we address two main challenges. First is the technical complexity of managing parallel streamers, and also difficult trade-off with the video quality and the latency as the second challenge. We define the problem as how to dynamically optimize quality and latency fairness for concurrent heterogeneous clients that rapidly join or leave the channels. And also we try to design the solution in a scalable manner. We present QuaLA as our main approach, that stands for Joint Quality-Latency Architecture. QuaLA consists of three main layers: in access layer, edge zone, and backbone. You can see in each layer we have different entities. In the access layer we have cells, VRPs, and in edge zone we have GCC as a global central controller and that coordinates all communication between cells. And we have the CDN network at the top layer in backbone layer. We design QuaLA in two versions: centralized QuaLA and distributed QuaLA. In the centralized QuaLA we just need the GCC to solve the problem. First we design the problem in mixed integer linear programming model, and then GCC run the model and find the solution. And in distributed QuaLA we ask the VRP to collaborate with GCC to find the solution in distributed manner. We also introduce two definition for fairness, QE fairness: fine-grained fairness and coarse-grained fairness. In the centralized model, we consider three main groups of constraints. First, the quality constraints, for example, which quality should be served by which CDN server, or the volume of transmitted data from source CDN server to cells. And also in this latency constraint, we propose four equations to satisfy the given latency by selecting optimal bitrate from CDN servers to the requesting cell. And also with the last two equations in the latency constraints group, where we satisfy the bitrate. We adjusted the bitrates from source cell to the CDN server. And the last group of constraints focuses on the available bandwidth of the cells, zones, and CDN servers. Finally, through defining the objective function, we introduce two definition of fairness: fine-grained regarding the minimum fairness of each live channel V, and in coarse-grained we consider the minimum fairness of all live channels. How does distributed QuaLA work? To design C-QuaLA in distributed way, we applied Proximal Jacobian ADMM method to mathematically split the MIP in the central model to all VRPs and GCC. So in each VRP we have a simple optimization model, linear optimization model that can be solved by each VRP, and then after finding the local variables, the VRP all VRPs send the variables to the GCC, and GCC update them regarding all gather information from VRPs, and then send them back to the VRPs again. This communication between the VRPs and GCC repeated in the limited number of time slots. To solve the problem in distributed manner, by applying the Proximal Jacobian ADMM, we first need to relax the binary variable L regarding two auxiliary variable X and Y, that is about the outgoing and incoming traffic to and from cells and CDN servers. And also we defined BCV as the required bitrate for downloading the video by cell with respect to the desired qualities. Then by having the linear form of the model, we can present the Lagrangian form of the linear model regarding the multipliers lambda and gamma, and also two penalty parameters rho 1 and rho 2. Then we can select which optimization model should be run with which VRP, and also GCC should update Lagrangian multiple lambda and gamma in each iteration. For the performance evaluation, we consider the 4 numbers of the video live channel and the limited number of the clients at each zone. And also we designed the GCC in Python, and also we have the CDN server to store the videos and to store the segments. Also, we define 3 main patterns of the priority for all bitrates. In the first experiment, we showed that the convergence time of the D-QuaLA, and you can see that regarding different values of latency, D-QuaLA reached to the global solution after 30 iterations. And also the performance of C-QuaLA and D-QuaLA regarding the defined fine grain and coarse grain fairness. You can see the maximum, the summation of the, for example, bit rates in the C-QuaLA fine grain is maximized. However, in the coarse grain, the minimum value of the video channel, the minimum value of the, for example, the minimum value of the fairness in video channel is maximized. You can see here for the fairness of the obtained by C-QuaLA fine grain and C-QuaLA coarse grain. And it's worth mentioning that D-QuaLA followed the trend of the C-QuaLA in all cases. In this work, we presented the QuaLA in 2 versions of in 2 versions of the centralized and distributed QuaLA, C-QuaLA and D-QuaLA respectively, and also we defined fine grain, coarse grain fairness. We showed that the C-QuaLA reached to the 57% improvement in the bitrates and the fairness at different scenarios. For the future work, we set 2 main directions. First, extend QuaLA to support learning-based approach and design D-QuaLA for fine-grained fairness. Thank you for your attention. I would be happy to answer your questions.